then you can build this up and you can get good efficiency at doing it. And as you build up the hydrogen on the surfaces and adsorb species, it will diffuse into the bulk of the metal, and so you'll build up the hydrogen or the deuterium in the bulk. Now, next slide, please. This is a crude model to show what the overall picture is, and now I'm going to try to emphasize some of the factors that may have contributed to the difficulty of reproducing experiments, and the fact, in fact, that even with well-established techniques that are for this, you don't always get the same results. The electron in the D3O, or in the case of alkaline solution, D2O, provide the D-adsorbed. That's an electrochemical process, and it's fairly well understood. It's even been studied on single crystal surfaces, like platinum and other surfaces. Some of that D-adsorbed by either of the routes goes to form D2 in the solution, and you can build up extremely high concentrations if your solutions are really clean, because there's a bubble nucleation problem. Then the D2 finally reaches the gas phase and comes off as you recognize it as gas. What we're trying to optimize is putting it into the bulk of the material. And that's the process that we work on. But now suppose that your palladium is run-of-the-mill palladium. It will have void structures, or you may create them in the course of charging it with deuterium, simply because the lattice swells, and then when you take it out fast, it can crack, and you leave these voids in your palladium. And I would suggest in that case, you've got to do some remarkable metallurgical work to either prevent that or to recure those voids after they've formed, in other words, to remove them. And many of the observers, I think, are coming to the conclusion that the metallurgy of the palladium is very important, and not just the chemistry, but the metallurgy. If you have a backside exposed that's not electrochemical, you'll produce D2 there too. And one of the things you can do is to put poisons on the surface that inhibit that. And you can, in fact, add agents to the electrode phase, to the palladium, to try to inhibit this reaction in the palladium phase too. And I think that's going to be the sensible direction for some of the work in this study. Next few slide, please. What I've said here is just sort of summarized. You want to promote this reaction, and you want to promote this reaction where the palladium takes up the deuterium in the bulk phase, and you want to inhibit any reaction that lets the palladium lose its deuterium in the form of D2. Next slide, please. This is a similar slide to the one that Dr. Bard talked about, and I think Dr. Stan Pons will mention it too, because this is a key feature. The overvoltage is equivalent to putting the system under a high pressure, but it's not the same exactly. What you do is to increase the activity of this hydrogen or palladium, deuterium in the palladium lattice relative to the value at 1 atmosphere by a very simple exponential function of the overpotential, the difference between the reversible potential and the potential the electrode operates at under the electrochemical condition. An overpotential of -1 volt looks quite accessible in the Stan Pons Fleischmann paper. It implies even higher than that can be obtained in the future. That's the equivalent of having an activity ratio of 10 to the 16.7. It is the equivalent of putting a pressure on of 10 to the 33.2, and I'll let you become an undergraduate physical chemistry student to know why those numbers differ. But it turns out that this is not necessarily achieved in a simple way, because you may have, as you change the activity in the lattice of the protons or deuterium, you may have a change in phase structure. You may get a large expansion. It's not true that it just shows up as concentration changes, because it's activity, remember, with an activity coefficient, and the activity coefficient can change drastically too. So this is the question: what really happens when we supercharge the palladium with deuterium? Next slide, please. Well, I thought it would be interesting to see what we would do in the way of identifying some of the guidelines to how to get a palladium or another metal that will take up large amounts of deuterium, presumably increasing the probability of the nuclear fusion by at least, we bringing them in closer proximity. You need a lattice that won't undergo changes rapidly, that's stable as all get out, where it takes tensions and stresses. It seems to me high melting points, not only of the pure metals, but some of their alloys, high solubilities for deuterium, high diffusion coefficients, and high tensile strength are all things that you want to look at and consider as qualitative guides in seeking out candidate systems, because there may be many of them. Freedom from voids, I think, is essential. You'd like not to have the free void structure. There are strong indications in the work, for example, of Horkins and others, that hydrogen, when you take it out of the lattice rapidly, produces stress cracking. And thereafter, the hydrogen diffuses very readily and through cracks and voids. That doesn't sound too good for this application. Then you want fast kinetics for this reaction and slow kinetics for the others. That requires a tailoring of the catalyst or the catalytic surface of the palladium to inhibit the reaction that you're not after. And then finally, you need stability against corrosion. I think that you don't want to. Next slide, please. This just to show you some of the candidate systems. And at the moment, the only ones that I think are well examined are the palladium and the titanium. But many have high melting points and boiling points and look like they would be candidates. And when you consider that alloys are fair game, and in fact may be attractive for hardening up the system, that means that you would have a very large amount of work to do. I think the electrochemist and the metallurgist, as well as the fusion chemist and fusion physicist, are going to be very busy people. Next slide. I'd like to finish just with the one really critical question. Can 2D pluses be injected into a given site using reasonable potentials, that is, reasonable overvoltage? And the overvoltage, if you put 2 in a site, corresponds to 46 kilocalories approximately. Is 46 kilocalories enough to get 2 deuteriums into an octahedral site? I think the answer is marginally no. Is it enough to get them into 2 tetragonal sites? Even less probable no. To get 1 into each, I think you can do it. Could I have the view graph, please, that I have at the end there? The operator said he would turn it on. This is a drawing out of a paper by Bob Bowman, but I think it wasn't quite intended for what I'm going to do, but it does it nicely. This is the tetragonal site. These are 2 octahedral sites. You go from an octahedral site to a tetragonal site and back again, and as you go over the tops of these barriers, there are more or less trigonal symmetry sites. You could see or imagine the species jumping from one side to the other. Now, if you could crowd 2 into any one of those wells, you'd be doing well, but I'm not sure you can. It looks doubtful. But you may get a considerable amount of hopping back and forth. And so maybe there is a kinetic factor. One wonders whether it's possible that they collide into each other if you have cross paths. And so that while the probability is very low, that there is some probability of collisions. Now, I think the factor that works against you to this is that the repulsive terms are so tremendous that a collision is very hard to accomplish. And therefore, that may not be a highly probable explanation. If you, on the other hand, had some localization of an electron in the lattice so that the 2 deuteriums, as they got close to each other, might have their potential energy repulsion lessened a bit, maybe it could be. Anyway, this is the type of speculation that chemists might engage in. What happens as these race back and forth? Well, these have been exciting times for electrochemists in the last few years. The superconductors really are not electrochemical, but you can make them electrochemical. And the work with the scanning tunneling microscope is certainly fascinating because of its ability to be used in situ in electrochemistry. And now we have a new challenge, fusion induced by electrochemical methods. I hope that your fever in this area of fusion fever stays high.